In this video, I'm going to be showing you guys how to do integration by parts. And I promise you, by the end of this video, you'll be able to solve any integration by parts problem, math problem you'll see on exam. I will cover every single common one that you'll see. Maybe this video will be like 20 minutes long because of that, but you guys got it. Just put down the phone, stop watching TikTok while watching a integration by parts video, and let's go ahead and start off integration by parts. So I need to clarify that integration by parts can only be applied in certain situations. So you're not going to use integration by parts with the integral of e to the x, right? You're not going to use integration by parts with the integral of x to the power of 3. That makes no sense. You can just use reverse product rule, power rule, or reverse, or it's just some identity, right? You don't need that. You can use integration by parts when you have two functions multiplied together. So it's sort of like the reverse product rule. That's why I said reverse product rule for you. See, I was thinking about that, but integration by parts is reverse product rule. And if I did a little bit of, I could show you the proof of where this comes from, this formula comes from for integration by parts, but I genuinely don't think that really matters that much. You can just memorize it, honestly. I memorize it with uv, vd, vu, right? And the rest are just replaced with, you just gotta remember the replacements of the d's. But integration by parts is used when you have two functions multiplied together. What do I mean by this? Well, if you have e to the x and the function x, these are two separate functions. You can't take the integral of this, right? So you can use something called reverse. You can use it like reverse product rule, right? You can use reverse product rule in this case, which is integration by parts. And in the case of x e to the x dx, in order to use integration by parts, you need to set something equal to u, hence the integral here, and set something equal to dv. Right? So right here, these two are analogous to the original function. Basically, what you're doing is turning some function with the format u and dv into the format to the right, where it's uv minus v du, some possible integral on this side, without integration by parts. But oh yeah, and sometimes you're gonna have to integration by parts with an integration by parts problem. So it's like chaining a chain rule problem. You have to use integration by parts again and again sometimes. But basically, in essence, integration by parts turns a function with the format u dv into uv minus the integral of v du. And in this case, we can set x equal to u and e to the x equal to dv. Now, the functions you pick as dv and du matter. The functions you pick as dv and u, matter. Okay? But I'll show you those tips when we're going into the problems. But basically, in essence, it's just whatever's easier to take the integral of, whatever's easier to take the derivative of. I'll show you what I mean by that in the problems. But you pick a u value, right, in the format u dv. And this time we're picking x as the u value. And you pick a dv value, which is e to the x dx technically. But you don't have to write the dx. You can kind of just omit that when you're showing work, unless your teacher specifically states otherwise. But what you can do is actually, well, if dv is equal to e to the x, well, you can take the integral of e to the x, right, to get v. And now you have your v value on the right side of the function. And if you want du, you can take the derivative of u, right, the derivative of u, and derivative of u is just x, so it's just 1. But you have to add dx here as well if you want, right? But basically it's just 1. And like in real, if you actually care about the mathematical notation, then you would put dx here. If you actually care about the mathematical notation, you put dx here as well. But basically what's happening is you see a d, that's just a derivative of something. You see a u, and you want to find du, just find the derivative of that function. Now, what we can do after separating u and v, right, and du and dv, we've differentiated these is, well, if the format of the old function was u and dv, we can separate it into uv minus the integral of v du. So let's write that down. Let's write u, well, our u value is x, v is the integral of dv, which is e to the x, minus the integral of v du. So what's v in this case? Well, v in this case is e to the x. What's du? Well, du is just equal to dx. It's 1 times dx, technically. So, just dx. Well, look what we have here. This is just an integral of e to the x, right? So, the integral of x e to the x is x e to the x minus e to the x plus c, of course the arbitrary constant, never forget that. But this is basically the first problem you're going to see, and this is a very common problem. X e to the x might be literally the first problem your teacher shows you in any single lecture. So when they're teaching you, this is a very common integration by parts problem because it's very simple and it can get and it kind of gets the idea across. But let's go ahead and work on another problem, which might not seem as obvious because there's not really two explicitly stated functions. Now, this problem is the integral of the natural logarithm of x. Super common problem. You're gonna see this as, again, this might be one of the first integration by parts problems that your teacher will show you, depending on the class, of course. Obviously, that's professor's preference. But this one is a little less obvious as the previous one. The previous one had two explicitly stated different functions, right? It was x and e to the x. You can easily separate that as u and dv, right? But this one, not as obvious. Why is that? Well, because technically, the integral of ln of x dx is equal to 1 times the ln of x dx, correct? Well, now we have two separate functions, 1 and ln of x. And the format of integration by parts calls for this right here. So, what we want to do, again, pick a value for u, and then pick a value for dv. So, when we pick the value of u, which one should we pick? 1 or ln of x? Well, we should pick ln of x, and I'll tell you why. Because if you picked ln of x dx for dv, then you would have to take the integral of the ln of x to find v, right? In order to find v, you need to take the integral of dv. Well, you can't. In this case, we're trying to solve for the integral of ln of x. How are we going to solve for the integral of ln of x inside the integral of the ln of x? So what you should do is pick ln of x as the u value. So all you need to do is find the derivative of u to find du, rather than find the integral of ln of x, which is not possible without another integration by parts steps. And what we should pick for dv is just simply 1 dx, right? So if we take the integral of 1, you get x. The integral of 1 is just x. So we have v. So the integral of dv is x, since dv is equal to 1. Okay, now that we have this, well, we can set up the problem. U minus v. So the ln of x, sorry, not u minus v. Why do I keep saying that? U times v. U times v is x times ln of x minus the integral of v du. So what's v? V is x. Du is 1 over x. Dx, technically. Well, we can rewrite this, so that's just the integral of, well, these terms cancel out. X and 1 over x cancel out. So all you get is 1 times dx. Well, the integral of 1 is simply just x. So this equals x ln of x minus the integral of x, sorry, integral of 1, which is just x, plus the arbitrary constant, of course, plus c. And right here is maybe the identity you saw in Calculus 1. So sometimes in Calculus 1, they're going to tell you the identity for the integral of the natural logarithm of x, right? And the identity is just x ln of x minus x. And you know, now you guys know how to actually compute that rather than memorizing it. So let's go into another problem. This one is chained. All right, you better watch this because you're going to get this on an exam probably. This is a very common exam problem. This one's a chained integration by parts problem. So yes, you have to use integration by parts in an integration by parts problem for this, but it's eventually possible. Bear with it. So let's go ahead and start this. Remember, as always in an integration by parts problem, you need u and dv. These are the two values that you start with because this is the equivalence of your integration by parts. So you have a function u and a function dv, you turn it to this. So let's go ahead and pick the u value. Which one's easier to take the derivative of? Which one's easier to take the integral of, right? Well, in this case, why would we pick cosine of x as dv if we can just pick e to the x as dv? And the reason why we would do that is because, well, if we want to take the integral of e to the x, well, that'd be very, very easy, right? The integral of e to the x is just e to the x. So why would we not take dv as e to the x? Because now v is super easy to calculate. V is just equal to e to the x. And then u will be our cosine value. So if you wanted to find du, take the derivative of the cosine of x, which is just negative sine of x dx. All right, let's go ahead and write down our equivalents. So we turn something from u dv to uv minus v du. Okay, so let's write down uv. U and v is e to the x times the cosine of x minus the integral of v e to the x du. Okay, du is the negative sine of x. So we can actually cancel out this minus here. We're actually bringing the minus of the sign out. And then we can have a function that looks like this. Okay, well, this is again another integration by parts problem. So let's go ahead and write down another u value and dv value. And let's keep this e to the x cosine of x in the back of our mind. So dv, which one should we pick? Again, we're picking e to the x since that's easier to take the integral of, which is just e to the x. And our u value is sine of x, therefore du is equal to the cosine of x. Now we just have to write down this equivalence again. So uv is e to the x sine of x minus the integral of v e to the x du, cosine of x dx. Now this might not seem as obvious right now what we're doing, but let's go ahead and combine these two equations. If the integral of this is equal to this, right? We just use integration by parts on this integral here. We can just combine these two equations. So e to the x cosine of x plus e to the x sine of x minus the integral of e to the x cosine of x dx. But remember, this is an equivalence, okay? So we set u dv equal to uv minus the integral of v du. So technically u dv in this case is our original integral, e to the x cosine of x dx. And look what we have here. These two integrals are equal to each other. So if we add e to the x cosine of x on both sides of the equation using a little bit of algebra, and yes, you can do this, you get, maybe if I were to clear up some space, I guess you guys get the gist of that already. You get e to the x cosine of x plus e to the x sine of x is equal to 2 times the integral of e to the x cosine of x dx. And the reason why I put 2 is because I added this term onto the other side. And since they're equal to each other, we can just leave the 2 in the front, right? You add 2 of the same things, it's just that thing multiplied by 2. And what we can do is, well, divide each side by 2. And let's clear up some space actually. I guess you guys, I can erase this. I can erase this, right? Yep, I can erase that. Thanks for responding to me. Okay. Well, what we can do here is divide by 2 on both sides. What we get is e to the x cosine of x plus e to the x sine of x over 2 is equal to, well, these are crossed out, is equal to the integral of e to the x cosine of x. E to the x cosine of x. So right here to the left is our integral in this case. Keep in mind, an integration by parts is an equivalence statement, right? It's an equivalence statement. So don't forget about the other side of the equivalence, right? The u dv part. That one's important. But let's go ahead and solve for the integral of arctan. Maybe you've seen that in your Calc 1 class, right? Okay, last problem. Now, if you don't understand the last one, that one's going to be on exam. I guarantee you, your professor most likely, why'd I say guarantee most likely? Okay, I should have just said most likely. But most likely, you're going to get a question like that on an exam. I had one like that on my exam. My friends had like that on different schools on the exam. I see the problem online a lot. So, yes, try to understand that last problem I did with the e to the x sine of x or e to the x cosine of x. But this one's also another common one, arctan. Arcsine is also a common one, but I'll cover arctan in this case. And again, this is implicitly has a 1 times arctan in it. And like any integration by parts problem, you want to use u and dv first. So which one should we pick as dv? Which one should we pick as u? Well, if you picked arctan as dv, you wouldn't be able to find v, right? You wouldn't be able to find v. So what you should do instead is pick 1 as dv and arctan as u. because you can find du in this case, but you can't find v in this case. So du is equal to the derivative of u, and the derivative of arctan is simply the identity 1 over 1 plus x squared. And v is the integral of 1, which is just x. All right, now that we have that, let's go ahead and set up the function. U and v are x and arctan of x, and v is x, du is 1 over 1 plus x squared. Well, if you combine these two functions, you get x over 1 plus x squared dx. Now, all you have to do is solve this integral. We already have this part. This part is part of the integration by parts, right? Why did I say parts multiple times there? We just need to find the integral of this. Well, you can use u sub for this. Let's go ahead and use u sub. We want to take u in the denominator, 1 plus x squared, and du is equal to 2x dx. Okay? Well, let's isolate dx. So the isolation of dx is equal to du over 2x is equal to dx. Now, if we set up this integral into terms of u, you get x over u, right? Since 1 plus x squared is equal to u, we can substitute that in. And we also substitute dx with du over 2x. What actually happens is these x's cancel, and the 1/2 can be factored out of the integral. So it's simply the integral of 1 over u du. The integral of 1 over u is just 1/2 the natural logarithm of u plus c. Well, u can be substituted in with 1 plus x squared. So let's go ahead and do that. And then you get 1/2 the natural logarithm of 1 plus x squared plus c. That is the integral of x over 1 plus x squared. So if we erase these things for space, basically these two are equal. Therefore, if we substitute the solved integral into this part of the function, then you get minus 1/2 natural logarithm of 1 plus x squared plus c. This right here is the integral of arctan using integration by parts. So hopefully this video helped. Hopefully I covered all the things, all the bases that you need to know. But as always, if you have any questions, put it down in the comment section. And if you found this video helpful, consider subscribing and liking the video. Thanks for watching.